In fact, we're just going to summarise on routing and move on to the next topic. So we've looked at what is routing. We use routing tables. We can calculate least cost paths. You can use algorithms like Dijkstra, Bellman, Ford and others to calculate the least cost paths. You don't have to do it manually in practice. So routing algorithms. Some of the strategies or the two basic approaches we looked at was calculate routing tables, use them, flooding as an alternate. There's a few slides on routing protocols and algorithms which summarises some of the stuff that we've already mentioned. We're going to skip straight to the summary, skipping this example. And this is a summary of both routing topic and also the previous topic on switching. We've introduced networks. We know what a communication network is. We connect devices across multiple links. Switching, going back to several weeks or 2 or 3 weeks ago, is the method for delivering data from source to destination across multiple links. We looked at circuit switching and packet switching. Stations are, or the end user devices are the sources and destination. Switches are special devices inside the network that connect via multiple links. We looked at circuit and packet switching, two different approaches for delivering data through switches. Switching is about getting the data from source to destination. Routing is about choosing the path to take. Routing is about finding what is the best path to get from source to destination, determine the path. And we've seen with routing, there are different metrics, different ways to measure what is the cost of a link, and therefore what is the least cost path. Different strategies. We've mentioned Dijkstra's algorithm, Bellman, Ford algorithm, there are others. And in fact, there are different protocols in use. The final thing we want to say, these are concepts, switching and routing, mainly applicable to wide area networks. A network across a city, across a country, between countries. Some of the concepts are used in local area networks, but definitely applicable to wide area networks. The next topic is on local area networks. And that's what we'll move to now. So now we want to look at what about communications inside an office, inside a home, inside a campus, local area networks, and some of the technologies we can use. We'll look at the basic ways that LANs can be designed, and then we'll look at the most common standard and technology used for LANs today. It's called IEEE 802, and in particular 802.3 is a standard for wired LANs, Ethernet, for example, what we use on a regular basis, and we'll look at that in some detail. But first we'll concentrate on just general approaches for how can we structure and design a local area network. Compared to wide area networks, which cover a large area, a large geographical area, local area networks, we're talking about over tens of metres, hundreds of metres, inside buildings, possibly between buildings in small cases, in some cases. So within a campus, a building or a home. In a wide area network, the network, that is the links, the switches in a wide area network, is normally owned and operated by a particular organisation on behalf of the end users. So, as opposed to a local area network where the cables and the switches are normally owned and operated by an organisation that the end users are a part of. So SIT, for example. SIT owns the cables going through the building, the switches for the local area network. We own the end user devices, the PCs attached. Okay, SIT doesn't own your laptop, but as a student here, it's as if you're a member of SIT. So the end user devices in SIT's LAN and the network is owned and operated by the same organisation. And it's designed by SIT. If SIT wants to add an extra switch and some more cables somewhere, then they go and do that themselves. In a wide area network, normally someone like SIT pays another company, a telecommunications provider or an internet service provider, pay them to use their network for a wide area network. So our connections between our two campuses, we pay an internet service provider for the connection under the ground between the two campuses. We don't own the cable going between the two campuses. We don't own the devices in the network there. So the wide area network is owned and operated by someone who's usually not the end user. Which usually means in LANs, the end users, we have more control over what type of design we can achieve. We can select the design and we can modify the design. Wide area networks are normally leased to users. Local area networks typically support higher data rates than wide area networks because they need to cope for both internal communications and external communications. So if we draw SIT's network, I won't draw in detail, but as a cloud, which is all the computers and network on this campus, and we have one connection to the outside world. The data rate of our internal network is normally much higher than the data rate of this link to the outside world. Because this internal network needs to support data being transferred between devices inside the network, as well as between devices inside and outside. This link only needs to support the data going outside. The network internally needs to support data going outside as well as between computers inside. That is, if I'm transferring data to a local database inside SIT, that doesn't go out to the internet, it's internal to our LAN. Our network needs enough capacity to support that. Also, wide area networks can have lower capacity than LANs because of multiplexing. And the fact that even though we may have 100 users in here, and each user can potentially send at 100 megabits per second, we don't need a very high capacity on this external link because in most cases not all users are sending at the same time. If we look at any 1 second in time and look at all the computers sending, only a small fraction will be sending at the same time, and therefore we don't need capacity on the external link to support everyone sending at the same time. Of course, there are some exceptions. You'll see some wide area networks with higher data rates than LANs, but we'll go through some of them towards the end of this topic. So how do we design a local area network? We want to cover a campus or a building. Some things we need to consider are the topology. How do we arrange the nodes? Or how do we arrange the stations? That is, the PCs that want to connect, the end user devices connect together. What transmission medium do we use? What type of cabling? Do we use cables or wireless? So what transmission medium to choose? And how do we control who accesses that medium? Because we'll see in some cases, in LANs, some of the transmission mediums we may use may be shared mediums. That means if two people transmit at the same time, then their data may not be delivered. So we need to look at ways how to control who can access a shared medium. So we'll explain that a little bit more after we go through the first two. First, how do we design the topology of a LAN? What options do we have? On links, we have two options. I have two computers, I can connect them on a point-to-point link, or I can connect multiple computers in a point-to-multipoint configuration. A local area network, it's not a link, it's a network that may have multiple links, should allow multiple users to communicate with anyone else on the network, with each other. There are some basic topologies, arrangements of the nodes to allow them to communicate with each other that we can go through. A mesh topology connects everyone to everyone else via point-to-point links. If we have 4 computers in our very small LAN, just 4 computers, if we use a mesh topology, how many cables do we need? We have 2 more quizzes. Is it 2? 2 more quizzes in the next 3 weeks. So we need to squeeze in some quizzes. Simple quiz question. In a mesh topology, 4 computers, we want to allow them to communicate with each other. If we only have point-to-point links, how many links do we need? Try to connect each computer to each other computer. We've got one answer. Anyone else? Assume they are full duplex links. So you've got a cable and you've got multiple 4 computers and you need to connect each one to each other computer. How many cables do you need? Point to point. A mesh, a full mesh, which means connect everyone again. 6? That's looking closer. By a mesh, or a full mesh, we connect everyone to every other node directly. Node 1 connects to node 2. Node 1 also has a link to node 3 and to node 4. So node 1 can communicate with node 2. They just send data direct. Node 1 can communicate with node 3, and same in the opposite direction. If they have full duplex links, and 4 can communicate with 1, 3 and 4 need a link between each other, so do 2 and 3, and 2 and 4. This is an example of a mesh or a full mesh topology. Use point-to-point links between every pair of nodes. And there are 6 links needed here. 6 cables to connect those 4. In a computer, we connect the computer to a network via a LAN card, a network interface card. So you plug the cable into the socket in one of these, which is installed in your computer or in your laptop. Let's call this is one LAN card or network interface card. How many do we need in a mesh network per computer? How many sockets? We need 3. That is, node 1 has 3 links going into it, so it needs 3 LAN cards, or 3 sockets at least. So in a full mesh topology, we have a point-to-point link between every pair of nodes. Remember, point-to-point, only 2 nodes connected to that link. So in this case, we need 3 network interface cards per station, per computer. 1, 2, 3. And in that way, we can communicate with anyone else. We just send direct. But it turns out that this approach is not very efficient because we need a lot of links if we have a lot of stations. Here we had 4 stations, 4 computers. What if we have, let's say, an SIT? We have 100 stations. 100 PCs that want to connect in a full mesh. How many links do we need? It turns out to be almost 5,000. The number of links needed, if we have 100 computers, if we want to do this, is almost 5,000. 5,000 different cables to connect 100 computers. And each computer would need how many network interface cards? How many cables plug into each computer? 99. That's not feasible. That is, I cannot plug 99 cables into my laptop or into my PC. So a mesh network doesn't scale very well and seldom used unless for a very small network. We'll look at the other 4 topologies which have been more common for connecting computers together. A bus, where we have a single cable, a bus, and everyone attaches to that. Like a communications bus inside a computer, you send onto the bus, the data transfers across the bus, and everyone attached to that bus can receive a copy. A ring, where we connect them using point-to-point links in some circular manner. A star and a hybrid topology can combine these in different ways. Mesh only suitable for very small networks. Let's go through the others. First, a bus topology. Here we have our stations, our 4 stations. They all attach to a special bus. Let's say 1 cable. It's a point to multi-point link. These links were point to point, one station to one other station. In a bus, it's a point to multi-point. This node can transmit. You can think it transmits onto the bus, and everyone attached can receive a copy of what they transmit, a copy of the data. So one transmits, multiple points receive in this type of topology. The terminology used in a bus-based LAN is that the way that a computer attaches to this bus is via a tap, and the bus is really a cable as some endpoints. So what we would do in a bus network, if we have our 100 computers in SIT, think we have one long cable that passes by every computer, and every computer connects onto that cable, onto that bus. And when my computer transmits, it transmits that data as a signal is sent across the bus, and every other computer, because the data passes by every other computer, any other computer can receive that data, or all computers can receive that data. Of course, normally I only want to communicate to one other computer, and so we'll use addresses to determine who, but we'll see address formats later. But the concept, transmit onto the bus, everyone attached to that bus can receive, because it's point to multi-point communications. You just send a signal and it's transmitted all along the bus. Everyone receives that signal. The transmission propagates through the medium and is heard by all stations. We need some special devices at the end of the link to terminate and absorb the signal. In our mesh network, the data that we send, and we'll refer to the data as a frame, like a packet. We have a frame with some data. And in a bus topology, our frame needs a header with an address. In a mesh topology, we don't necessarily need addresses. If node 1 wants to send to node 2 in this topology, it just creates a packet and puts it onto this link. There's only one other station attached to this link, and it is node 2. So there's no real need for an address to get the data to node 2, because only node 1 and 2 are attached to this link. Therefore, if node 1 transmits, it's guaranteed node 2 will receive, not node 3 or 4. But in a bus topology, and we'll see in the other topologies as well, we need addresses with the frames. Because if we say A, B, C and D, if A transmits a frame, everyone receives a copy of that frame. But if A wants to send data to C, B, C and D will receive a copy if we include the address of the destination in the frame, C. Even though B and D receive a copy, they'll look at the address and say, okay, this is not from me, I'll discard that frame. C will receive a copy and see, okay, I am the destination, I will take that frame and process that frame. So in a multi-point communications, we need addresses to identify who is the destination. In comparing the same characteristics as what we did with a mesh, you can think we have one link here, one cable. So one cable passes by all computers. So that's an advantage. With a mesh, we needed 6 links for just 4. Here we just need one cable for 4 stations. For 100 stations, we just need one cable. Except the cable becomes very long. Place a cable in this campus such that it goes via every PC. It needs to go via this room, to the next room, to the next room, downstairs, and keep going, and even to the other building possibly. It becomes very complex to do that. Each station only needs one attachment to that network. Each station only needs one network interface card, as opposed to our mesh where we needed multiple network interface cards per station. So there's an advantage of this compared to a mesh. Generally easy to install bus topologies. Because of this, we just need one cable, one network interface per station. But the medium is a shared medium. If 2 stations transmit at the same time, we'll have a problem. Try and draw that. Here's our bus. If station A transmits onto the bus, then it's sending a signal all the way along the bus. Everyone receives that signal. If station D transmits at the same time, it also transmits a signal on the bus, all along the bus. As a result, these stations receive, in fact, the combination of those 2 signals. They interfere with each other, and it makes it very difficult for the stations to understand or to distinguish what did A send, what signal did A send, and what signal did D send. We generally call this a collision. If 2 entities transmit their data at the same time on a shared medium, then that data collides and no one can receive successfully, no one can understand. So in a shared medium, we need some way to control who transmits. That's medium access control. So we need some protocols to share the medium in this case. In the mesh, we didn't need that. If node 1 transmits to node 2, at the same time, node 3 can transmit to node 4. They're on different cables, those signals. They will not interfere with each other. And similar, 2 can be transmitting to 3 at the same time. So there's all point-to-point links, no interference between the different transmissions on the different cables. That's not true with a bus topology. Another problem with a bus topology is if this is our bus and there's a fault, there's an error on the bus somewhere, at least none of these pairs of nodes can communicate with each other. That is, A cannot reach C or D. And normally in practice, if there's a significant error on this in the link at this point, no one can use the bus. Whereas in our mesh topology, if this link fails, 1 and 4 cannot communicate, but everyone else still can communicate. So there's a difference in terms of how can we tolerate faults in the network. Having one cable having to pass by many stations is a problem because our signals cannot necessarily propagate a long way. Usually there's a physical limit of how long our bus can be. So that's another limitation. Therefore, we usually limit the number of stations that can attach to the bus. A bus topology was used in the early wired local area networks in buildings, the Ethernet networks, but has actually been replaced by a star topology. This just shows the transmission of a frame. C wants to send data to node A. It creates a frame with some data and a header with the address of the destination A, transmits it on the bus. We can think that that frame passes along the bus. Everyone can receive a copy. B sees the frame going past, notices the frame, but notices it's not the destination, so effectively ignores that frame. A receives it and takes a copy. That is, it receives, and if it's extended along here, the frame keeps going. So everyone receives or can potentially receive a copy. Only those that are the destination take a copy of that frame. An alternate topology, a ring topology. Connect our 4 stations by unidirectional point-to-point links in a loop, in a ring. So here are our 4 stations, and these are point-to-point links with these black squares are repeater devices. They repeat if something's received, if we go in this direction only, if this station transmits, is received, and this device repeats the signal across this link, and then across this link, and back across this link. The frame travels around the ring. The station's attached to repeaters so that if this station transmits a frame, it travels in one direction around the ring. Everyone can, or the frame passes by every station. Again, we need an address in the frame to indicate who is the destination of that frame. This one illustrates that, where we have C again transmitting a frame destined to station A. Just in this example, the ring direction is from C to B to A. C transmits on a point-to-point link to B. B receives, checks the destination, notices it's not the destination, transmits on the point-to-point link to A. So C sent to B, the frame effectively passes by B. B sends it on to A. A takes a copy. A sees the frame. I am the destination of this frame. Take a copy of that frame, process the data. But also A sends it on the next point-to-point link, in this case back to C. C was the original source. When C receives the same frame again, it takes it off the ring. It doesn't send it on again. So even though A received and was the destination, it still sends it on. That's a very useful feature if you want to send a copy of one frame to multiple destinations. For example, if we had 10 nodes and C wanted to send it to 2 of the other 9, it would send, and 2 of those stations would take a copy, and it would just flow around the ring once. So it's a very efficient way to to multiple destinations by just sending one frame around the ring. How many links do we need? Well, here we need 4 point-to-point links with our simple case of 4 stations. There are 1, 2, 3, 4 point-to-point links. Each device has this, or each station has this repeater device. Again, that could be built into the computer, into the network interface card. So you could think that each computer would have a network interface card or 2 network interface cards. So 2 cables plugged in, because this computer has a cable coming from this node and also from this node. We receive on this cable, transmit on this cable, go around the ring. Sorry, other way around in this case. We go in this direction. Much simpler than our mesh, almost the same in terms of complexity of links and network interface cards compared to the bus, slightly different. Again, it's a shared medium network. If 2 stations transmit at the same time, then those transmissions may collide with each other. And as a result, the destination stations will not be able to understand what is received. So we need some way to share the medium amongst the stations. Traffic flows in one direction. That can be inefficient sometimes if you have a large ring. It can take a long time to get to the destination. Some old LANs, 10, 20 years ago, used ring networks. IBM had a token ring network. We'll give an example later. Today, some metropolitan area networks, MANs, networks that connect across a city, for example. Let's say a company has multiple offices across the city. They need a high-speed network connect between the offices. They may have a metropolitan area network. Often rings are used in those scenarios, and even in wide area networks, ring networks are used. They're very good in terms that it's very easy to detect where a fault is. If this link is cut, then by sending a frame around the network, we can detect, okay, the frame went across these 3 links, it didn't go across, it didn't get to the destination, therefore we identify the fault is on this link. That's very useful if we want to have a network which is, say, passing by tens or hundreds of nodes across a city or across a country, and we need to detect errors very quickly, like in a matter of milliseconds. So nowadays used in city and wide area networks. Last example, star topology. Connect each of the stations to a special device called a hub, a switch, or a repeater. Again, we use point-to-point links. This is a point-to-point link to the central device, as is this. Normally we have either a duplex link or 2 unidirectional simplex links, so we can send to the central device and receive at the same time. So full duplex link, for example. And what we do is, to reach any other destination, we transmit to the central device. That central device sends it to either one or all of the other devices. As a result, the data will be received by the destination. We have addresses included in frames. If this is A, B, C, and D, if A wants to send to C, it creates a frame, send it to the central device. One option is that the central device sends a copy of that frame to all 3 other nodes. And this one will receive it, sees that it's the destination C, take a copy. These 2 would receive a copy, notice that they are not the destination, and ignore that frame. An alternative option is that we send the frame to the central device notices that the frame must go to C, and simply sends it direct to C. We'll explain a little bit more about the differences later. How many links do we need? One per station in this case. If we have 100 computers in our network, each computer needs a cable going to the central device. So that's much better than our mesh and almost similar to the other approaches. So we don't need so many links. We don't need more than one network interface card. One network interface card per computer. Except for the central device. That needs one network interface card per end user station. This central device has 4 cables plugged into it. If we have 100 stations, it would need 100 cables plugged into it. If one link fails, if this link fails, of course this station cannot communicate with anyone else. The link has failed. But these 3 can still communicate between each other. So that's an advantage of using this topology. That's not present in the previous 2 cases, in the ring or the bus topology. The problem, a con, is that this depends upon the central node. If this device fails, our entire network fails. So that's a problem in this case. This is the topology used in most local area networks today. This computer, does it have a cable? If it did have a cable plugged in, there will be a cable plugged in. It will connect to a socket in the wall, which the cable goes down to the 3rd floor. In one of the rooms in the 3rd floor, there's a special switch there, this central device. And a cable plugs into that. And same from the computers in the other rooms. All have a cable back to that central device. So these are small switches. This one has 8 ports. You can pass around, it's very exciting. This is an 8-port switch. It's a box. Of course, wireless access points, don't drop this one, it works, is a switch as well, or contains a switch. That is, you've seen these devices before. Sometimes your home ADSL modem will have a switch built into it, where you can plug multiple computers in a star topology. In larger networks, you'll have a switch or a central device that supports 16 or 32, maybe 48 ports. And you have multiple switches. In the Macintosh lab, in the technician's room, if you put your head inside there, you'll see a rack of switches with many cables plugged in. Or in the network lab, you'll see some switches in those cabinets. These are using a star topology. So that's, 5 options. Full mesh, seldom used, not used very often because too complex in terms of the number of links and number of network interface cards. A bus topology, we have one link and everyone attaches to that and sends across that one bus. A ring topology, we send around between the stations in a ring. A star topology, where everyone sends to the central device. Or a combination of them, some hybrid, where one portion of the network uses a star topology and another portion of the network uses even a mesh topology. So you can combine them in different ways to get more complex topologies. They're the basic options we have in designing a LAN, and the most common one used today is a star topology. What about the transmission medium? What about the cables that connect between the stations and possibly the central device? There are many different factors that will impact upon what's the best choice. There's no one best option. Depends upon what reliability you want, what sort of performance do you want in your LAN, what's the layout of the building, the structure of the building, because we need to install the cables in a building. We don't want to put them along the floor, so we need some way to put the cables into walls and so on. Common cases of different transmission media in LANs, not always the case, but it's commonly coaxial cable. We've mentioned this before the midterm. Coaxial cable is often used in a bus topology. In the earlier LANs, you ran a coaxial cable between the different computers to form a bus topology. Optical fibre, not so much in local area networks, but more in metropolitan area networks. Optical fibre is used in a ring topology, so across cities. So we're moving away from LANs in that case. Usually when we need very high speed. So sometimes connecting not end stations to switches, but a switch to another switch, we may use optical fibre, where we need very high speed. We'll see some examples of where that can be done later. And twisted pair, copper wires in a twisted pair arrangement, commonly used for star topologies. The LANs that we have today, all the LAN cables, and we saw before, these cables that you plug into your computer are using twisted pairs, copper wires, so electrical transmission over 4 pairs of copper wires there. They are generally the cheapest and easiest to install. If you want to put a cable through the cavities in the walls and through the ceiling cavities, then you need to be able to have them to bend easy. And sometimes you need to be able to cut them and join them together. And twisted pair is very good for that. It's very easy to cut and join together, as opposed to optical fibre. If you cut it, you need special equipment to join them together. So twisted pair is commonly used. So we need to choose a topology for our network. We need to choose a medium to use. And we've said in some of those topologies, or in fact most of them, the practical ones, we have a shared medium. If 2 stations transmit at the same time, the signals will interfere with each other and nothing will be successfully received. So, if that's the case, what we need is medium access control. If 2 stations transmit at the same time, we get what's called a collision of frames. If station A transmits a frame and station C transmits a frame, at the same time, those frames, we say, collide with each other. The destinations cannot receive those frames, we assume. Nothing's received. That's a problem. We want to avoid that. The way that we avoid it is to implement some rules such that only one station transmits at a time. And that's what medium access control does. It controls, or protocols or rules that control which stations access the medium at which time, with the goal of avoiding collisions so that our data gets to the destination. What the medium access control techniques do is try to give stations opportunities to transmit. If we have 10 stations in our network, one way to control to avoid no collisions is allow station 1 to transmit all the time. Do not let stations 2 to 10 transmit. That would work. If we allow one to transmit all day, the others cannot transmit, then there will not be collisions. But it would be unfair. Station 1 will get to transmit all the time, the other 9 stations do not get to transmit. That's unfair to those other 9 stations. So we need something that is both fair and efficient. We'd like some rules such that if we have 10 stations over a period of 1 day, each station gets an equal opportunity to transmit their data. So there are different approaches for doing that. The techniques can be centralised or distributed, and fixed or dynamic. 15 minutes remaining. We need 4 volunteers. Volunteer 1, come up the front, please. Who else? Volunteer 2, wake up and come up the front. 3 and 4. Thank you. Quick. Hurry up. Number 2, come on. 3 and 4. You're our stations. 4 stations, and you need to transfer data. So let's look at ways at which we can control access to the medium. And in fact, a good example of a shared medium is wireless. When I talk, if someone else talks, then the 2 transmissions interfere and the people cannot understand correctly. So that's what we have here, a wireless medium. If any station transmits at the same time, let's assume that we have a collision and they'll have to retransmit their data, which is inefficient. So a medium access control technique would, the stations follow some rules with the goal such that they get to transmit their data, but no one transmits at the same time. First example is round robin, where round robin means you take in turns. Let's say that your data that each of you want to send is your name. You want to transmit your name. We don't care who to, but you're going to say out your name, but you're going to say letter by letter. Each frame that you transmit, if this was a frame, contains some data, and the data you're going to say the first letter of your name, like S. And that's the transmission of one frame. And then later you'll transmit the second frame, T, and then E, and so on, but you'll transmit your own name. Your goal is to transmit your full name. First name will do. But you need to transmit one frame at a time. And the first rule, or the first scheme we'll follow is round robin, medium access control. And we'll do it in, let's first try a centralized manner. In a centralized medium access control, there's one device that controls who sends. I'm the central device. So I'm going to tell which station, I'm going to tell the stations when they can transmit. This will be easy, this one. So when I tell you, you can transmit the first frame, and when I tell you again, you can transmit the second frame. You can transmit. The data you want to transmit is your name. You need to transmit one letter at a time. Let's try again. You can transmit. Doesn't matter who transmits, transmit on the microphone. One letter at a time. So what we do is we take our data, our name, and we break it into frames or packets and transmit one frame at a time. You can transmit.
C.
You can transmit.
T.
You can transmit.
N.
And you?
N.
And now with round robin, we simply come back to the first one and take in turns. I think you can see that you would say the second letter, and so on. So that's round robin in a centralized approach where I'm the special device in the network, such as a switch, and somehow I tell each station when they get a chance to transmit, and I just rotate between them. We can do the same but in a distributed manner. If we had a ring network, form a ring. Form a ring, that is some sort of, okay, arrange yourself. And we're going to go, imagine they have cables between them. They could hold hands, but we won't need to do that. They have cables from here to here, here to here, here to here, and here to here. And they're going to go in this direction. In a ring, we go in one direction. We transmit in that ring. We're going to try round robin, but use a distributed approach. There's no central controller, and we'll use something called token ring. The idea here is we have a token, the pen. And the rules are, when you have the token, you can transmit one frame, and then you pass the token on to the next node. And they follow the same rule. Go. We're going in this direction. Transmit your first letter, pass the token. Second letter. And they will keep going. So this is round robin still, take in turns, but it's distributed. There's no central device. The nodes themselves have a special rule such that they know who gets to transmit. If you have the token, you can transmit. It's fair. If they had the same amount of data to send, they all get equal opportunity to transmit. So over a period of 1 minute, the first station we get on average 15 seconds to transmit, the second one 15, 15 and 15. We divide the time amongst the 4 stations. Next example, reservation-based, easy. Again, let's assume we have a central device, me. Reservation, the stations tell me you want to transmit both your first name and your second name. That's the data they want to send. But they only send one at a time, so first name and then second name. But what they do is before they transmit, they ask the central station for opportunities to transmit. And what they ask for, or they reserve opportunities to transmit based on how much data they have. So if someone has a name with 6 characters long, they'll ask me for an opportunity to transmit 6 times. Let's try this. Here we have a centralized, I'm the central controller. The first step is each station tries to reserve opportunities to transmit by asking the central device for opportunities based on how much data. How many characters do you have to transmit? First name, think about it. So you would send a special message to me asking me to transmit 10. She would send a special message to me asking to transmit 10 frames. And the second node would ask me... Okay, I would then make some decision. I have 10, 8, 7 and 6. I would decide which opportunities I would give to who. Maybe I think this node is more important. Maybe he corresponds to the most important in the set of stations, and I would say, now I'd tell them, okay, you're going to get 3 opportunities, you're going to get 3, you'll get 6, and you get 3. I would tell them that, and then they would transmit. So you would transmit the first 3 letters of your name. You would transmit the next 3 letters. You would get 6. And you'll get 3. And then I could go again and say, okay, you get another 3, maybe I'll give you 2. I would make a decision based upon the characteristics of the network and the stations. So they ask for opportunities, they reserve opportunities to a central device, and then I allocate those opportunities. Reservation-based MAC. Last one, or last example, random. Distributed approach, I'm not involved. You have to transmit 1 letter at a time. But the rule is, if you hear someone else transmitting, in your head you must choose a random number between 1 and 10 and wait that many seconds before you try again. So if 2 people say their letter at the same time, both of them will choose a random number and wait that amount of time. If I choose 3, I would wait 3 seconds, 1, 2, 3, and then try to transmit my data, my character of my name. Understand the rules? You want to transmit 1 letter at a time, but if you hear someone else transmitting, wait some random period of time and try again. Go. You want to transmit 1 letter of your character at a time. Let's try again. Just choose a random number if you hear someone else transmitting when you go. There was just about a collision there. 2 said at the same time. Keep going. Don't look at each other. Shut your eyes. Don't look at each other. You're in a network. You maybe a computer on the other side of the campus. You don't see each other. You just follow your own rules. Keep going. What's he doing? He just transmitted 3 characters at the same time. Good for him, bad for everyone else. So he transmitted multiple characters, 1 then immediately another. That's first against the rules. The rules should be which I didn't say, so that's okay. The rule should be you transmit and then wait some time before you transmit again. And that's designed so that it's fair to all of them. That is, if one transmits, the idea is that one transmits, and then because the others wait a random amount of time, this one may wait 3 seconds, this one 1 second, this station 10 seconds, the node that chooses the smallest random amount of time to wait, 3, 1 and 10, this one waits just 1 second and therefore gets to transmit. And then they'll do it all again. They'll wait a random amount of time, and because it's random, on average, each station will choose the smallest number out of the set, equal amount of time, and get to transmit an equal amount of time. One more time. Transmit your name. Had a collision. Keep going. He's cheating, but that's all right. Eventually they'll get there. It's very simple because there's no central device involved. I'm not involved. They just follow the rules, transmit. If someone else is transmitting, wait for some random time and then try again. They don't need to pass anything between them. They don't need to know what the other stations are sending, except whether they're sending or not. And eventually they'll get to send their data. It can be inefficient because this one transmits and then waits some random time and then transmits again and waits another 10 seconds and transmits. So it takes a long time sometimes to transmit their data. And there can be collisions. Two stations may transmit at the same time. A collision means retransmission, which is bad for performance. But it's very simple from the station's perspective, or at least from a computer's perspective. 3 examples of medium access control. And that finishes for today. Thank our volunteers, and we'll finish on LANs tomorrow. Thank you. So we'll move on to the last topic of LANs and finish that tomorrow.